This is Forest Guy Builds. I'm John, welcome to the forest. In today's build we're going to optimize my heat recovery unit. We're going to save energy by making it more efficient and at the same time increasing our comfort by making it more quiet. If you're a little bit handy, you can do the build completely by yourself. I will guide you through step by step. Let's go in and I'll show you everything about this awesome project. To give you an idea about the structure of this project, I'll run quickly with you through the agenda. I mark the chapters on the timeline, so if there is a specific topic that gets your interest, you can simply move to there. Those are the topics and high level what will be covered there. I'll show you my heat recovery unit and I explain clearly what all the downsides are if you use it out of the box. I'll explain clearly what improvements that we're going to do, so you can decide if this build is also interesting to do by yourself on your own implementation. If you are not familiar with what a heat recovery unit does, I'll explain it exactly, because in that way the improvements that we are going to do make way more sense. The main job of a heat recovery unit is ventilating the house. And to have an idea how much it is ventilating, we want to measure the airflow. You can buy a meter off the shelf, but it can be quite expensive. So I'll explain how you can create a cheap one for about 25 euros by yourself. In that way you can fine-tune the system, so it meets exactly the ventilation demand of your house. I'll go with you through the parts that I used, so you can decide what you exactly need. I'll show the ones that I bought off the shelf and the ones that I designed and created myself. And I'll tell you how to create that for yourself or to buy them. In this project there is a lot of automation and I'm not going to explain you how automation works in Home Assistant. There are many videos explaining that in detail. My assumption here is that you already have some experience with Home Assistant, and otherwise the skills that you need for this project, you can easily learn them by searching around, and otherwise just ask me. To wrap up the project, I'll go through the costs of the components and I'll give my conclusion if it's worth it, looking at the costs but also looking at the effort. This was the first project that I created a real guidance video about. And I had so much material that when editing I was struggling a little bit with the correct order. So I shuffled around some of the topics, and where I thought that something was missing, I created a voiceover and I added it. And maybe that looks a bit messy, but I did my best to make an as clear as possible guidance video for you. If you have ideas how I can make my next video even more clear, please let me know, drop it in the comments. All your feedback is really appreciated. I'm making those videos to inspire others, and my goal is to make them as clear as possible, so that they are useful. Enough introduction, let's go to my HRU and I'll explain you why and what we are going to improve. Let's go! This is the Daaldrop HRU that I installed several years ago in my house. I'm still happy with it, but over time I discovered that there are quite some improvements possible. The improvements that we're going to do are not rocket science. The more complex or expensive devices have them by default. This device is by default not really smart. It's not adapting to the CO2 level in the house. Based on the CO2 level, we can define the exact ventilation need of the house. If there are more people in a room, the CO2 level will raise. And based on the CO2 level, we can exactly identify what room has the ventilation need at that moment. So, by default, throughout the day, that will be for example the living room, and overnight it will be the bedroom. If we can modify our system in such a way that it is only ventilating the rooms that's necessary, we are saving energy on the device itself, we are reducing the heat loss to outside, and we're making the device more quiet, because the fans are only running on a speed that is necessary to keep a healthy climate in the house. And that's exactly what we're going to do. We already measure the CO2 level in the house with sensors throughout the rooms. We're going to talk to the API of the HRU to tell it the exact desired fan speed. By installing those simple manual valves in our existing air ducts, we can control the exact airflow to the individual rooms. And now they're manual controlled, but we can automate those with small servos. And those servos we can control with an automation system like Home Assistant. So if we see an increase in the CO2 level of the living room, we can open a valve to the living room, letting an increased airflow go to the living room and a reduced airflow to the other rooms where it's not needed at that moment. Same for the bedroom overnight. It is really convenient if the living room is not occupied throughout the night. The airflow will be closed and to the bedroom it will be opened. The big benefit here is that the HRU needs to run on a way lower speed to keep the climate, to keep the air quality in the bedroom on a healthy level. And this really reduces the noise level that the device is causing overnight. And to make this all work together, I had to design some components, 3D printed them, and there were many iterations before I had a solid working setup, but now it's working smooth. And those are the valves controlled by the servos with my 3D printed parts. It's now running flawless for several years and it's saving me in general a lot of energy, but it also drastically increased the comfort by having a more quiet device overnight. For those not that familiar with an heat recovery unit, I want to explain some of the basics about how it works. That will really help in the rest of the process if we are making our improvements. Lighting here is quite bad, so please don't blame me for that. I just want to give you a good explanation and I'm using my whiteboard for this. So here I have the graphical representation of a heat recovery unit. It has 4 flow inlet or outlets. The air flows cross in the middle. They are not mixed, they are separate circuits, but there is where the heat transfer takes place. So a really simple example. Outside it's, let's say, 5 degrees. Inside it's 24 degrees. Then the air that is going out of the house is about 20 degrees. It's always a bit less than it is in the living room, for example. The air coming from outside is about 5 degrees. Then the air that is going out, the 20 degrees, it's heating up the fresh air from outside from 5 degrees to, let's say, about 70 degrees. And the hot air from inside, it's cooled down till about 8 degrees. And this is the important part. Inside we have our hot air. Outside we have the cold air, but with a very low CO2 level, healthy fresh air, and that is heated up till about 70 degrees. So there is the efficiency. And because there is always some loss here, it now also makes sense that we don't want to extract too much air, because there is always loss. So if the device is running on a too high airflow, we are losing more hot energy than is necessary. Those numbers we can also use to make some calculations for the efficiency of the device. And we can make a nice representation on our Home Assistant dashboard. This is also the visual that I'm using on my Home Assistant dashboard. I will go a little bit in more detail about that visual, but that's not part of this project. To understand the exact airflow to the rooms, we need a meter to check it. And we can just buy those off the shelf, but they can cost about a few €100 or more. Because this started just as a hobby project for me, and I only need it once, I thought I'll create one myself. So I bought this quite cheap airflow meter. I think it's about €25 or something. But the issue is that we only can measure the airflow and not the amount of airflow. To measure the volume of airflow to a specific room, we need to catch all the air from the air duct and let it flow through the meter. The out-of-the-box devices have a sort of hood that can be attached, or that is like part of the device itself. It's quite simple to make something by yourself by using this. And this is one that I didn't modify it yet, but if we cut one part from it, and if we make a small wooden plate, or we can 3D print it, and this is attached to each other with some pressure, because it needs to be airtight, and it's not exactly airtight, but it's good enough for this. And the meter, it will just fit here. And hey, for this purpose, it's good enough. It's just to measure the differences between the rooms. So it works like this. When we put it together, and then we have a quite simple and cheap solution that we can use to measure the airflow per room, to compare them with each other, and to see if our concept is working. And by measuring the amount of airflow to a specific room, we can exactly define how far we need to open the butterfly valve Based on the air ducts on my attic, I will explain how this works in my setup. In this way you can expand it to the number of rooms that you want to ventilate. This is the blueprint of my small house. There is a bedroom, bathroom, living room, entrance hall and storage. My HRU is in the attic. This is a simplified visualization. My supply goes to the bedroom and to the storage, and there are 2 supply air ins in the living room. In this HRU there is only 1 fan running, so it balances automatically. It will bring in the same amount of airflow as it will extract to outside if the inlets or outlets are completely open. So the inflow we will control via the dampers. For every room that I want to control, I installed 1 damper. So I installed 1 for the bedroom and 1 for the living room. As for my storage room, I skipped that because it is not in use. It's always open a little bit so that it has a little bit of ventilation. There are cases that it's not so easy to control per room because there are several outlets after each other. For example, if you have this set up. In this way, if you have the damper installed before the 2 outlets, you will control them both, of course. If you want to modify your setup so that you can control per room, it's not that hard, but there is some more work, of course. The simple thing that you need to do in that case is make a branch of the main channel. And don't do that with a 90 degrees band. On my simplified visual there are 90 degrees bands, but in real life always use 45 degrees. It will give you a better airflow. So make a breach here and have it to the additional room. In that way you can place the additional damper there and you have a total system of 3 dampers. Important to say, normally you control the amount of airflow via the outlets. But in this case we control the total flow via the dampers. So that means that I have the outlets always fully open. The bedroom outlet is completely open and the living room outlets are completely open. I'm not an expert in those ventilation systems. I just tried out what works. And for the last years I have a system that I'm really happy with. So for me this works and I hope it's also useful for you. If you have suggestions or idea how to make this even better, or if you're going to implement this in your own house, then let me know. I'm very interested in how this works out for others. If you just implemented this in your own house, it's really fun to play around with the airflow meter to see what the exact airflows are if you close or open a valve, a damper, or if you increase the speed of the HRU and see what it exactly does. Because then you can really control what needs to go to which room, when. And you can really search for the balance between the required amount of airflow and the acceptable noise level of the HRU. And of course it also depends on the amount of people in the house, the amount of people that are sleeping in the bedroom. Because that has a direct impact on the CO2 level and the required ventilation. It's no surprise that with 2 people in the bedroom, the HRU needs to spin its fans faster than when there is only 1 person sleeping there. So the related noise level will also a bit higher. But at the bottom line, it is way more efficient if it is ventilating overnight only the bedroom where the ventilation need is, instead of also ventilating the living room that is completely unnecessary at that moment. In the next example, I'll show how I'll measure the airflow in the room, the volume that will be refreshed every hour. This is one of the 2 air inlets in my living room, and I'm going to use this one to show you what happens with the velocity if we change things. We simply put the device that we created over the air outlet, and we see that it's already measuring the wind speed. Now it shows about 1.1 meter per second. This is with the bedroom open and the living room open. I made a simple Excel to convert the meter per second to cubic meters per hour, the amount of refreshed air per hour in a specific room. I now close the living room and let's see what happens with the velocity. It will drop to about 0.3 meter per second. And if you would expect that it went to 0, that's not the case in my situation. Because as you maybe recognize, the dampers that I have don't fully close. They always have a little bit of gap on the side of the butterfly valve. So there is always a little bit of airflow, even when the damper is in its fully closed position. And I think that's not a bad thing. It will always provide a little bit of airflow to every room. As long as I can control the majority of the airflow, this is okay for me. Now let's see what happens if we open the living room again. We see that it goes back to about 1.1 meter per second. And now the interesting thing, let's close the bathroom and see where it then ends. It will go to about 1.5, 1.6 meter per second. As for now, I kept the HRU on the same power. I only wanted to confirm that the dampers are working as expected and that the airflow goes to the rooms that we choose. If we increase the fan speed of the HRU, then of course to that specific room there will be an even more increased airflow. Those are all the components that you need for this project. I will go through them quickly. It all starts with the ESP8266. I use it on a breakout board, so it's easy to wire. To control the airflow by rotating the damper, we use a servo. And while 90 degrees should be enough for a servo, I'm using 270 degrees, because I had some issues with the 90 degrees ones. My ESP Home and Home Assistant code are based on the 270 degrees servo. To prevent hassle, I would suggest if you do this project, just use the 270 degrees like I did. While the ESP can run on a USB cable, the servos need 5 volt, so we need an additional 5 volt power supply. But as the ESP8266 can also be powered by 5 volt, it's sufficient to use the same power supply to power the servos and the ESP. I will show in the wiring how we do this. For this project, I use a simple 5 volt power supply that I had laying around. Although it's not mandatory, I like to put stuff in a box so that it's resistant against some dust and is just some more rigid. For those kind of small electronics projects, I'm using those kind of boxes. They have some breakout ports on the side so that you can put the wiring through. The wiring is not going over a very long distance, so we can keep that quite thin. I'm using 0.5 mm for this. And although I used 2-core wire for this project, if you need to order, I would suggest that you take 3-core wire for the positive, the ground and the signal to the servo. And of course we have one damper per room that we want to control. Keep in mind that the damper needs to be in the same size as your air ducts. I'm using 125 mm. That's also the size of the air ducts on my attic. As I think this is a damper that is widely available for a 125 mm channel, I can imagine that fitting will differ per brand, for example. I'll give some more details about the exact measures on the website, so that you can verify that the 3D printed parts have the right measures for your type. If your dampers have a different size, let me know. If there is more demand for a specific size, I can simply try to design some parts for that specific measure. Besides the parts that I now showed you, we have of course the PCB that is installed in the HRU. It's a small PCB that makes it possible to control the fan speed. The one that I have is specifically for my HRU, the Ito Daaldrop one. For you that can be different. So double check what PCB you exactly need to control your HRU. As the 3D printed parts that we use to control the dampers take quite a big role in this project, I think it's interesting to see a bit more about that. I will show you that via the tool that I use to design them. This is Tinkercad.com, the tool that I use to do the design of my 3D parts. And I will not waste your time by doing the real-time design on the screen. But because the 3D parts are quite an important component of this whole project, I think it's interesting to see a little bit more about it. Here you see the individual components, still existing of negative and positive components. If you join them, they will become one. And you will see the final part. Here I'll show you around all the parts a little bit and I'll move them to the position that they later will be mounted. This is how the gears fit together and how we transfer the movement via the clip to the damper in the air duct. This gives you an idea about all the parts in its final position. I will make the files of the 3D parts available for you, so that you can simply print them by yourself. If you don't have a 3D printer or you want to support me, I'm thinking about offering those 3D parts in a sort of set on my website, so that you can just buy everything in once. Initially that was not my idea, but if there is a demand for it, I can investigate the possibilities. If you like this kind of content, then please like this video, but also take a look at my other videos. There is a lot to discover, and there is even a lot more to come. And although this didn't start with a commercial mindset, it would be awesome if I can continue doing those kind of projects. Help and inspire others by doing the same. This summarizes the chapter of the parts used, the ones that I bought and the ones that I created. Now let's move to the code in Home Assistant. I split it up to make it a clear structure that I can guide you step by step through. I will guide you through in a structured way. First up, I'll show you the helpers that I created in Home Assistant and why we need those. Second step, I will create the automation based on the helpers that we created. In the third step, I will connect the ESP82 to the servos and I will power it up. And I'll show you exactly what is in the code that we flash the ESP with. How it is working, what it is doing, and how you can make it also more adaptable to your own situation. To test everything, I created a small dashboard and I will show you what happens if the CO2 levels in the rooms change. If everything is working as expected, the servos should rotate and we can simply pick up the ESP and the servos and use them on air ducts on the attic. So let's go. We start with the creation of the helpers. Helpers are like fictional entities in Home Assistant that we can create by ourselves. They are not a physical device. I created them here already and I created two helpers from the type input boolean and I call them home HRU bedroom and home HRU living. Those are our indicators to what room the airflow is active. Then I created two sliders from the type input number and I call them home HRU slider servo 1 and servo 2. Those sliders we need to adjust the servo to the desired position. I'll show you briefly how I created those. Create helper, and those first two are from the type toggle. I will cancel it now. And the sliders are from the type number, and then we give minimum 0 and maximum 100. And then it looks like this. It's just a slider from 0 to 100. And with this I want to open or close the damper in the air duct from 0 to 100%. This is also your foundation if you don't want to work with full open or full close dampers, but with like a percentage of it. Briefly showing how you will get there. Settings, devices and services, helpers. So let's start with the creation of the configuration for the ESP and do the flash. And afterwards we will create the automation. So I will create the new device. Continue. I will give it the name Home HRU Control without dashes. In my experience that is less prone to errors. It's an 8266 that we're going to use. And we will just install it. I prefer to do a manual download so that I can flash the ESP via Windows PowerShell. So it's complete and it asks us to save the file and we can close this. And now we see that the Home HRU Control ESP is online. If we click Edit, we see the configuration of this. And now it only contains the basic configuration, so nothing related to the servos that will control the dampers in the air duct. We will add that configuration manually. And I already prepared that, so I will just do a copy paste here. And I will also provide that configuration so that you can use it to modify it for your own setup. And I will guide you through everything which is necessary in the level of detail that is at least minimal needed. So at the top we see the name of the device, Home HRU Control. The board that I'm using is the Node MCU version 2. There is some basic information in it that I just left there, like the API encryption key. Then there are the things that we really need for what we are going to do. So I'm adding those services, Control HRU Servo 1 and Control HRU Servo 2. These are just the same sections that will control each one of the servos that we're going to use. OTA, I just left it for what it is. This is also added manually. HRU Servo 1, output PWM. Transition length 5 seconds. And this is something that I added myself because the servos by default move quite fast and then they make more noise. If I give them a transition length of like 5 seconds, they move slowly and they make way less noise, which is convenient. This section I also added. It are the two GPIO pins that we will use from the ESP device. So I'm using GPIO 2 and GPIO 4. And when I show you the device, I will show you the pins, but always make sure that for the ESP device that you are using, you're using the right GPIOs. The section for Wi-Fi is how the ESP device will connect to the Wi-Fi that is in your house. And I prefer to make use of a static IP, but by default it is DHCP. If you also want to make use of the static IP, you can just add this section. The enable fallback hotspot is also by default available. If the device cannot connect to your home's Wi-Fi, it will create a Wi-Fi that you can connect to do some repairs. Captive portal is also there, I just leave it. I will do an install, a manual download, like I also just did. And this time it takes some more time to compile it, because we added a lot of additional things. So we'll just save it as the same name. I'll override it, keep. We will close this. I will go back to the PowerShell and I will do a flash with the same file. I'm using COM3 and this path, but for you that is different, of course. So the flash is completed. Let's go back. Let's close this. The device is still there. And I will just do a ping to verify that the device is up. The device is up, so that should work. So now the services that we created on the ESP should be available. And the next step is to create the automation so that when we adjust the slider for a servo, that it really operates that way. And I already created the automations for this, so I will also do a copy paste here and then show you exactly what is in. I will create two for each servo one. So the name of the automation is home HRU control servo 1. The entity ID is input number home HRU slider servo 1. This is the slider that we created, the helper. So if that slider changes, this automation will be triggered. And this is the action that will be done. So ESP home.home HRU control, this is the ESP device that we just created or that we just gave a config. And control HRU servo 1 is the service that we approach. And we save this. Yes, for this I just create another one, the second one. And as I used a convenient naming convention, I can also make it very easy here for myself. Servo 2, servo 2, servo 2. And this will do the job. So we have those two automations now, which should take care of when we adjust the slider that the servo is moving. And let's try that. So I just limited the automations related to the servos in the top here. And you see that they are triggered like an hour ago. I just created them, but they were there before, and that's why they show a bit like a last triggered. If I now open a slider here, this is the first one, and I adjust this, we see that the automation is triggered. So now we see that the servos are operating based on the sliders. That was the first automation part. This is the automation that takes care of opening the damper to a specific room based on the CO2 level. So we have triggers. When the bedroom or the living room, the CO2 changes, this automation will be triggered. Then we have two possible options. The first option is if the CO2 level of the living room is higher than the bedroom, it will turn on the home HRU living helper that we have created, and it will turn off the bedroom. And this is very important because otherwise the servos will do nothing. They need to change the input number of the sliders that we created. So in this case, we use servo 1 for the living room, servo 2 for the bedroom. So it will set the input number for the slider of servo 1 to 100, and it will set the slider for servo 2 to 0. And for the second one, we have exactly the opposite. So if we have a higher CO2 level in the bedroom than in the living room, it will turn off the helper for the living room, turn on the bedroom. It will set the slider for servo 1 to 0, and it will set the slider for servo 2 to 100. In YAML code, it looks like this, and I will provide the code in the notes here or on my website so that you can easily copy paste it and modify these sensors and entities to your own devices. And now let's see if this all works. To test and show this, I created a small dashboard with the helpers that we have, the living room and the bedroom. Now in the background we see the automations. And here I will simulate the CO2 levels in the rooms. So at this moment we see that the living room is 634 and the bedroom is 497. So the living room is higher, and we see that also active here. Now let's simulate that the bedroom is higher. Let's make that like 800. Then we see that it makes the bedroom active. And the slider is modified and the servo is rotated. So it opens the damper to the bedroom. At the moment that the living room has a higher CO2 level, everything changes the other way around. This is exactly what we want. So now it's opening the damper to the living room to provide all the fresh airflow there, and it's cutting off the bedroom. Maybe obsolete to say, but those buttons don't do anything by themselves. I created them now as just identifiers to see, to verify to what room the airflow goes. If we want, we can also create automation that when we press one of those buttons, the airflow to that room will be opened. But that's not the purpose of our automation, because we want to make it completely automatic that the airflow will go to the room with the highest demand for fresh air. So we don't want to do anything manual. If there is a need for this, then let me know in the comments, because I can simply create that or give an example how to make it manual adjustable. And if you want to see how to configure this for several more rooms, I can also create some guidance video about that. And for this concept, I wanted to keep it as simple as possible, so that you just can try it out and see how efficient it works for your HRU. I will attach all the red wires together to have the positives connected to my lab power supply, which I have here. I will attach the grounds together with one additional wire to have it connected to my ESP. Just make sure that you do this, because if you don't connect the ground of the servo's power supply with the ground on the ESP, it can give you some issues. I'm going to use the first yellow wire of the first servo, and I will connect that to my D2 pin. And D2 in this case is GPIO4. The signal wire of the other servo I will connect to the D4 pin, which is the GPIO2. So we wired everything. Let's see what happens if we power it up. I will power up the ESP via the USB. And I will turn on the power supply to have the 5 volt to power these servos. So everything is up, and let's see what happens. Here we have the test setup, and let's see if everything works. At this moment the living room has the highest CO2 level. So let's turn that around and let's make the bedroom the highest CO2 level. Let's make that 800. Set state. And we see that the identifier for the bedroom becomes active and that the servo is rotated. So that's exactly what we want. Everything works technically now. We can simply take those servos in this ESP and install those on the dampers in the air ducts on the attic. So let's move to the installation part, and I'll show you how that works. And here we make a side step. Before installing the parts on the air ducts, I'll explain how we talk with the HRU to control the fan speed. I'll show you the interface of the HRU itself and the automation in Home Assistant. So what we need to create to make the API calls and how we do the actual control based on the CO2 levels of the sensors in the house. The sensors that I'm using are mostly Netatmo weather stations, the modules for indoor. You can also use other CO2 modules, of course. Everything that exposes the CO2 level in a room can be used for this automation. So configure your own CO2 sensors to make it automatically controlled on the CO2 level in a specific room. In the meantime, if you have questions, drop them in the comments and I'll try to help you. Let's proceed with the API of the HRU. We installed the PCB in the HRU. And that way we can contact it via a website. Here you see the interface of my i2Daaldrop. I will show only the relevant and most important things here. At the moment that you're able to reach this page, showing you the settings of the HRU, you're able to control it via an API. Let's go to the API part. Here is some information how it works and some examples. The IP address given here is an example. We reach it via the 2.11 in my case. For your case, this is different. And let's do a test here, if it works. We go to the main page of the HRU and we see that it now has a fan speed of 15. I will give the comment in the sidebar to control via the API the fan speed. And I will test with a fan speed of 72. It says OK and we go back to the main page to verify. Now we see that it has the speed of 72. So that works. And this means that we can control the HRU via our Home Assistant, via a so-called API call. I'll move to Home Assistant and show you how we create all the required API calls. In your configuration.yaml file, you can create those API calls. And this section is relevant for what we want to achieve here. So I created several lines here to adjust to a different speed. I created one for 100%, 75, 50, 25% and a 10% which is for me a silent mode. For me those numbers work. With your device you can play around by yourself. You can try out different settings and see if the device is quiet. If you want to do this really detailed, you can measure the total airflow out of your HRU and adjust the percentage based on that. For me, this works. Now we are also able to control the fan speed of the HRU based on the CO2 level. Let's go to the attic and do the actual installation of the parts and see if it all works. Those attics are quite often not that spacious, so it can be a struggle to do a good installation. Because I already did this a while ago, I saved myself the hassle to remove the damper from the air duct. But I can quite easily explain what needs to be done here. This is an air duct coming from my main channel, from the fresh air. It goes to one room. So I simply cut the air duct in half with an angle grinder or cutting disc. If you cut it in half, there is space to insert the damper. After mounting the damper, we can install the 3D printed parts and the servo. So this is the correct order. The small clip goes first, then we have the part that's keeping the servo in place, the ring that will keep the gear on the damper stable. Now we can use the screws to tighten it. Double check that the clip you put on the damper is in the middle. You can slide it a little bit by just using the screwdriver. We mount the gears as last. First I'll connect the servo with the wires so that we can bring it to a starting position. I have the damper for the bedroom open, so I will also open it now on Home Assistant. The servo is now in line with how we want the damper. So we place those two at the same time and we fit them together and we press them on the servo. Do a double check that you didn't accidentally move the damper. So this is its starting position, it's open. Let's see if it does what it should do. To make it more clear how the rotation goes, I just put this here. Now let's close the valve for the bedroom. And that's exactly the 90 degrees rotation that we wanted. Install this also on the damper to the living room and you have a nice balanced automatic system that only ventilates the rooms that are necessary. And with this we finish the build of today. So let's do some evaluation. Let's go through the costs and see if it's worth it. To control everything, I'm using an ESP8266, which is about €3. We use one damper per room, and in my setup there are two, and I'm using that as the example. Mine are 125 millimeters, so depending on the size, the price can vary also a little bit. This size is about €17 each. We also need one servo per room, so for the setup, those are two of about €8 each. The PCB that is installed in the HRU is specifically for my device, so it can vary per device how expensive this part is. But I'm using mine as an example, which is about €35. And there are some small other things, like the cable, a power supply, a breakout board for the ESP, the 3D printed parts, and some screws to tighten everything. It's difficult to define the exact cost of this, but let's say that this is €15 in total. And this is optional for the technical part of the project. But if you want to measure the airflows per room, you can buy like a funnel for just a few euros, and the anemometer will be about €25 or something. So in total, that's also less than €30, but it's optional. So it's about €125 in total if you want to do the technical implementation with the materials that I used for the 125 millimeter air ducts. And if you also want to fine-tune the airflows per room, it will be about €150 in total. And then the question, is it worth it? Looking at the costs, about €150. I think that's a really good deal. Because you are increasing your comfort by making the device more quiet. You're making it more energy efficient, so it saves a bit there. But I think that the biggest gain is in the reduced heat loss. Because you are only ventilating based on the minimal demand, on the minimal needs at that moment. But my personal favorite is the more quiet device overnight. And looking at the effort that you need to put in this project, yes, it takes some time. But that's also the nice thing of those kind of projects. It is exactly how I designed it, and I directly see the benefits of it. I completely understand the system, and I can fine-tune it wherever I want. I can expand it with an additional room if I want, and because it's a completely open system, I can modify all the parameters that I want. So if I want an increased airflow at 800 ppm instead of 1000 ppm, I can simply modify that. Or maybe in winter, when it's really cold outside, I accept a higher ppm, I can simply make some automation there, that it overrules when it's extremely cold outside, for example, so that it drains less available heat in the house overnight. These are just some examples that are the benefits of an open system like this. You can modify whatever you want, so I'm curious what you will do with it. If you have ideas, let me know, drop them in the comments. That summarizes this build. I hope you are as excited about it as I am. If you're going to build it, let me know. If you have questions, drop them in the comments. And as for now, this was Forest Guy Builds. I'm John, and I hope to see you in the next project.